All right, ray diagram practice problem number 1. We're going to start applying the thin lens equation. And just because it's thin lens does not mean it doesn't also apply to mirrors, because the equation still applies. The focus being the fact that it is a thin lens. That's what we were talking about in the last section, where you don't have to worry about one curve and then another curve. You just go to the central axis and you assume there's only one curve because the lens is so thin, it's really not changing that much inside of the lens, or changing its direction that it's moving. So you can safely assume there's only one bend instead of two, even though both bends are assuming you always have convex convex or concave concave. Both bends are always going to be in the same direction, in or out out. The other equation we're going to be applying is the equation for magnification. Magnification is the absolute value of image height over object height, which I think you should be able to derive that intuitively, despite the fact that it's on your equation sheet. Magnification times as big as the object is going to tell you how big your image is going to appear. So if your magnification is 3 times me would be 18 feet tall. That's what my image would appear as if it were projected out of a projector. So my image height would be 18 feet tall. And magnification is also equal to negative image distance over object distance. I really don't think that the negative sign is a great way to think about it. I think you should think about it intuitively going forward. And just use absolute value of image distance over object distance, and knowing whether it's going to be upright or inverted based on your ray diagrams. Your ray diagrams are going to become more and more important. All right, all of that being said, let's get to work. Where's my blue? A little person is standing 30 centimeters in front of a converging lens with focal length 10 meters. I want to know the location of the image. I want to know whether the image is upright or inverted. And I want to know if it's a real or virtual image. So you want to, when you do these ray diagrams, for them to have any value at all, they have to be pretty darn close to scale. If you can use graph paper, you're going to be absolutely set. But even if you aren't using graph paper, if you're close enough to scale, it's going to work well enough that you can solve the problem. As I said before, always start with a crude diagram. So I'm going to pull out the crucial information. 30 centimeters in front of a converging lens, so converging lens is also important, and focal length equals 10 centimeters. Converging lens, the lens that brings the rays together, converges them. At this point, you should be very comfortable if you see converging lens, you should know what it means. That's going to be your convex lens. In fact, I'm going to draw that a little bit bigger so we don't get crammed on space. So let's draw our converging lens. And I'm going to use my meter stick to draw the principal axis. In fact, I'm actually going to start drawing to scale exactly as I have up here. I'm going to put my 50 centimeter mark right here in the middle. And the person is standing 30 centimeters in front of a converging lens. 30 centimeters, that would put the person about here, standing upright. And it has a focal length of 10 centimeters. So the focal length is going to be right here on this side, and I'm going to draw my focal length behind the lens as well. And now you just follow your 3 rules. Again, I'm going to go back and draw my crude diagram over here. Person standing, parallel, goes towards the focal point. Rule number 2 goes through the focal point. And number 3, right through the center of curvature. So it's going to look something like that when we're done with it. Now my question is, why did I use that focal point? I should have asked that question before I drew it and let you think about it, but now I'm going to ask it the other way. Why did I use that focal point? Because with a converging lens, the rays are going to come together on the opposite side. If the rays come together where you expect them to, keep in mind a lens, the actual rays are going to be on the right-hand side. That's what you expect. That means everything's good. That means you're going to get a real image. And at this point, you should already know that the image is going to be inverted since it's below your principal axis. So I already know it's going to be a real image. It's going to be inverted, which means all we really have to calculate is the location. So let's follow our 3 rules. Parallel to principal axis and then through the focal point on the other side. So parallel to the principal axis and then through the focal point. Rule number 2, through the focal point and parallel to the principal axis. And since the rays are where we are converging on the side we want them to converge on with the lens, we're going to go through the correct focal point, or rather the left focal point. The left focal point. That's pretty good. And then parallel to the principal axis. And rule number 3 is right through the center of curvature. And hopefully this line will converge with our other 2. That's pretty good. That's pretty good. So the top of the person's head's rays are going to converge right here, which means the top of the person's head, if we put a screen right here, is going to be right there. There's his body and there's his legs. And you can already tell the magnification should be less than 1 because that person looks small. If you draw your ray diagrams, it'll tell you pretty darn well if it's big or if it's small. In fact, I'm even going to measure this distance to know ballpark what we're hoping the object distance will be. I'm guessing, or I'm sorry, the image distance. The image distance should, based on the measurement, be roughly 20 centimeters. That's what I'm hoping, based on my ray diagram and based on the image. It's also inverted, and it's also a real image because it's showing up over on the right-hand side for a lens, where we expect it to show up for a lens, where the rays converge when they're real rays. They aren't bouncing back over here. So now let's apply our equation. By the way, the other thing I forgot to tell you is I switched the variables we're using. We're using S's because your equation sheet uses S's, so I'm going to be using S's going forward. So 1 over the image distance plus 1 over the object distance equals 1 over the focal length. At this point, it's plug and chug. 1 over, I'm going to start with my base equation, and then plug in my values. The image distance is what we're trying to solve for, so 1 over SI, plus the object distance, 1 over 30 centimeters, equals 1 over the focal length, 1 over 10 centimeters. And if my math is correct, we get an image distance of 15 centimeters, which is pretty close to what we have based on my drawing. My drawing is probably a little bit off, well, it's definitely a little bit off based on that math, but pretty good. So now we have an image distance and we have an object distance. So question number 4 that I'm adding right now is, what is the magnification? Magnification equals -1 over SI over SO. You could have also used absolute values. Equals negative, oh, I'm going to go with absolute values. That's what I asked you to do, so that's what we're going to do. Image distance is 15 centimeters over object distance of, I think it was 30 centimeters. So our magnification equals 0.5, or 1/2. So an image will appear half the size. So if this person's 6 meters tall, they're going to appear 3 meters tall. And that comes from that equation right there. Magnification times the object height equals the image height. Thank you.